All right, guys, so this is one of the final practice problems that we want to finish out our unit with. It's going to tie together concepts of energy conservation, concepts of momentum conservation, and it's just a really good walkthrough of all the things that we've talked about so far. So here's the situation. We've got physics Fido. He weighs 20 kilograms. He's riding a skateboard 2 meters per second to the east, and he's catching a stick, or he comes across a large stick that's 5 kilograms traveling 1 meter per second to the west, right? So they're going in opposite directions, which he catches in his mouth. Okay, so I've drawn a kind of before and an after situation. We want to know how fast is Fido and the stick system moving after the collision, how much kinetic energy is lost during the collision, and then what is the efficiency of that collision. Right? So to focus on this first question, how fast is the Fido stick system moving after the collision, we are going to have to refer back to concepts of momentum, right? Because remember that momentum is always conserved during an interaction. It never goes away, right? So to figure out momentum, we need to find out what is the mass and the velocity of both Fido and the stick before the collision, right? So writing out everything that the question tells us, the mass of Fido is 20 kilograms. The mass of the stick, on the other hand, is 5 kilograms, which is a very big stick. The velocity of Fido, he's going 2 meters per second to the east, okay? Whereas the stick is going 1 meter per second to the west. Now, because they're going in opposite directions, we are going to end up dealing with momentum. I should specify that my velocity in the westward direction is negative. That just means that it's going in the opposite direction of Fido. Okay? So now with our mass and our velocities, we can calculate the momentum of both Fido and the stick before the collision, right? Just using our trusty momentum formula, mass times velocity. So the momentum of Fido, 20 times 2 is 40, and that's kilogram meters per second. The stick, on the other hand, 5 times negative 1 is negative 5 kilogram meters per second. Again, the negative signifying that they're going in different directions, opposite direction. Okay? Now, with this information, we can also figure out the kinetic energy before and after the collision, but we'll save that for later. Okay? Right now, because I'm looking for the speed of the system after the collision, I need to understand what the total momentum is before, because I know that the total momentum before a collision is always equal to the total momentum after a collision, right? The total momentum before is always equal to the total momentum after. So the total momentum of the system before the collision, 40 plus negative 5, that's going to be a total momentum of 35 kilogram meters per second. And I know that that's going to stay the same both before and after the collision. Okay, so 35 kilogram meters per second doesn't change. And we can use this to solve for velocity, right? So we're looking at our total Fido and stick system afterwards. Recognize that this system has its own mass, its own velocity, and as we just talked about, it's got its own total momentum. Okay? Well, since the total momentum in this case is only dealing about two objects that are stuck together, we can assume that these are basically one object. So the total Fido stick system, their momentum is, again, 35 kilogram meters per second. Okay? And we know that both the mass of Fido and the mass of the stick, when they combine, we're just going to add those masses together. So we found their combined mass of 25 kilograms. And we can use our momentum equation, right, to solve for our missing velocity. Okay? So we've got 35 is equal to the mass times v. Okay? So to solve for v, we're just going to divide our momentum by 25, and we should get 1.4 meters per second. Okay, so that's 35 divided by 25, and that should give us 1.4. Okay, so now that we have their total momentum, we have their total velocity, now we can actually figure out how does the kinetic energy change. Okay, so we've got this first one. How fast are they moving after the collision? We said 1.4 meters per second. Now we want to know how much kinetic energy is lost during the collision. So we know that we've got two moving objects before. These guys are still moving afterwards, so we have kinetic energy in both cases. Okay, so let's figure out the kinetic energy of Fido and then the kinetic energy of the stick. Okay, remember that our kinetic energy equation is 1/2 times the mass times velocity squared. Okay, so if we plug in 20 for the mass and 2 meters per second for the velocity, we should get a kinetic energy of 42.5 joules. Okay, so Fido alone has, oh, I'm sorry, I skipped that. Jumping steps here. If we use our kinetic energy equation, 1/2 times mv squared, we should get a kinetic energy for Fido of 40 joules. Okay, we're going to use the same equation to solve for the kinetic energy of the stick. Okay, and we should get 2.5 joules. Okay, so now that we have the energy of both Fido and the stick before, we can combine their energies together to figure out the total kinetic energy. Okay, now unlike momentum, okay, energy is scalar, which means direction doesn't matter. So to figure out the total, I'm just going to add 40 plus 2.5. So that should give us 42.5 joules. Okay, so there's our starting energy. And then we're going to use the same kinetic energy equation to figure out the energy afterwards. Okay, taking the new mass of 25 and the new velocity of 1.4. Okay? And if you crank those out, you should get a kinetic energy of 24.5 joules. Okay, 24.5 joules. Right? So that is going to be our final total kinetic energy. All right, so we've got that one figured out. We got their speed, we got the kinetic energy. So now we want to figure out how much did we lose, right? Here was our starting energy, here was our final energy. So to figure out how much we lost, we're just going to take 42.5 minus 24.5. Okay, and we're getting 18 joules. So overall, we've lost 18 joules. Which makes sense, right? Because we started off with two objects with a lot of motion, and then the overall velocity was reduced. Okay, so if we lose some velocity, we're going to lose some kinetic energy. All right. The last question is, what is the efficiency of this collision? Right. So this is kind of a weird question, but it means basically the same thing that we've always referred to as efficiency, right? What is the energy that we're getting out of the system versus the energy that we're putting into the system? Okay. We know that we lost some kinetic energy, so that's going to tell us that we don't have a 100% efficient system, right? We're losing energy in some case. So to figure out how much the efficiency is, we'll take the energy that we got out, okay, which is 24.5, versus the energy that we put in, which is 42.5. Okay, then we're going to divide those two numbers and finally multiply by 100% to get a full percentage. Okay, so I'll rewrite, I'll just kind of put this up here just so we can see it. The energy out, we said, was 24.5 joules versus the energy in, which is 42.5 joules. Okay. We're going to take that ratio, then we're going to multiply it by 100%. Okay. And you should get an efficiency of 57%. Okay, 57% efficiency. That's the total energy that was left over, or the percentage of energy that was left over after this collision. Okay. So types of questions like these, again, we are tying together a whole lot of different concepts, right? We're still dealing with our momentum equation. It's very, very helpful to predict speed before and after a collision, just because it's always going to be conserved. But then we're still keeping in mind how energy changes both before and afterwards. And we can use those energy changes to calculate efficiency. So I hope this was helpful. As always, if you have any questions, please reach out, and thanks for watching.